It is a given that in the future, space exploration is going to be affordable. So we need to improve the way where we are meant to make activities in the case of going to Mars. Two of the main problems we have to face is the data acquisition and the human positioning in early Mars expeditions. MDRS crew 126 developed the data acquisition module. This is a system that consists in three small systems: a master device, multiple slave device, and a portable gadget. What it is meant to, in early Mars expeditions, to positionate the humans in Mars near the base. How does this work? Well, the master device worked as a computer tested at the MDRS station. Multiple slave devices were in near the base in a pattern of having all the area controlled by the signals, and a portable gadget that every astronaut or crew member has in their life support systems. Why is that? How does this work? The portable gadget carried by the crew members broadcasted repeatedly beacon signals. So once the master device wants to know the ubication of a crew member, it just see which the slave devices are activated, and the position is can be computed as the intersection of the range of each activated slave device. It worked out pretty well, but they faced one big problem. Strong desert winds moved some of these slave devices from the ground, so once they were not in the position they were meant to be, the whole system didn't work out at all because they couldn't make the intersection between the slave devices. They suggested developing small mobile robots with a built-in slave device so they can produce a flexible network. That's why I started thinking about designing a rover that can fulfill this problem. So what is the rover meant to? It is meant to transport and install small loads and also instrumental, such as the DAM module. How is this going to do it? At our rotation as the crew 169 at the MDRS, we tested our project, each of us, and my project consisted in a rover that is meant to install the DAM module in the ground in order to prevent the strong winds to move it. So this is our crew: Moya Salazar, Elizabeth Centurion, Norbert William, me, Marcos Bruno, Celeste Valladares, Luis Ibanez, and Orson Lazzo. Each of us developed our own projects, and they all work pretty well. Well, as I told, this is the data acquisition model transportation rover. It is meant to be a low budget robot, so it can be easily constructed. The software of the robot, it was programmed using just Arduino. That is, it has free access, so anyone can program in Arduino. The hardware, well, as I was telling, was an Arduino Mega. That was the controller of the robot, and multiple motors shield, so all the motors of the wheels can be controlled, and 9-volt battery, so the Arduino can get its power supply, one and 9G servo motor for the camera, 2 big servos for the arms of the robot, 4 generic DC motors with their own wheels, 1 stepper motor, so it can the model can be installed on the ground, 1 LiPo battery of 5,000 milliamperes and 7.4 volts, and LDU93D controller to control the stepper motor, magnet bars, and because of the high price of the camera, we opted to use and just a cell phone. to be it easier to anyone who wants to implement this to use it, because anyone has a smartphone, and the software needed to make a live stream is free on the web, so anyone can do that. Also, because of the low budget, we opted to make our own RC controller. It was all made by ourselves. It consists in some buttons, a 5-volt regulator, and the controller itself. How it is meant to for the rover to work? As you see, the arms are supposed to carry the DAM model that is this cube that is with the same dimension. It's a 3D printed cube with the same dimensions and weight as the original model. It has a screw in it, so once the arm can grab it, it fixes it on the ground by using the stepper motor to fix the screw on the ground. As you see, that's the part where the camera goes. The cell phone, in this case, it was also 3D printed, and it can be easily modified by anyone to fit any phone or any camera. Well, the arms itself, 3D printed too, and well, that will be the main way of the robot robot while working. Here you can see an early video of the first EVAs, where it was not completely fixed all the problems it had. And see, that's the way it fixed the screw on the ground. The stepper was fully working. And the way to take this the screw off, so the robot to leave the cube over there, so the robot can go by itself. As you see, a problem over there in the first EVAs was that the cube was not fully on the ground installed. So on the first EVAs, we saw a number of limitations. First, the size of the remote control. Something that we didn't thought about before was that the control was really small for the size of the astronaut gloves. So the first EVA actually was 5 minutes long, because once I was in the desert, I couldn't try the RC controller because the glove was too big for it. Once I tried to push a button, I was pushing all of them. So we went to the MDRS lab, and we started working to fix it. After that, a second limitation, as you saw in the video, was that the magnet strength, it was actually too big. That's why the cube didn't install fully, as you see in the image. Once it was installed on the ground, once the robot was meant to go and leave the cube over there, it couldn't, because the strength of the magnets was too big. So what we did was cuting the bars that was meant to that. As you see there, that was cut off. Cuting the metal bars actually brought a magnet. The power of the magnet was decreased because of all the heat that was in the magnet. So because of trying to cut them off, all the kinetic energy was converted to heat. So the magnet power was decreased, and that was intentionally. That's what we wanted. And then after a few EVAs and trials, we can see the cube installed correctly and really fixed on the ground. So the high winds and also any other physical force can get it off. After that, we started to test how the live stream by using a computer, an open software that is available on the web, and an open app that any cell phone can be where any cell phone can be installed. We tested the app on the cell phones, and we got a live stream over approximately 42 meters of the MDRS hub. After we test that and everything was working on, the test consisted in to see a correct slave device transportation to transport the cube in higher and low and highlands, and with some inclination to see if the rover didn't turn over or anything. Secondly, the correct slave device installation to see if actually was fixed correctly on the ground. And finally, the device extraction to see if the rover can easily go out and leave the device where it is meant to be. The observation we saw over there was that the slave devices were installed correctly in 9 different locations. Why is this? Because there are different kind of soils in Mars as well in the Utah desert when we tried this, and we wanted to prove it in the max number of places to see if it works really well in each of them, and actually it did. Well, red resistance was found to strike the slave device, so that was what we meant to. It was really hard to take the slave device from the ground to prevent it, the extraction because of high winds. A bad thing we saw was because of the weather of the desert was that the servo motors were really hot after 10 minutes of work. So we must proceed to go to any shadow, for example, the one provided by the hub, leave it there like for 10 minutes so it can cool down, and then keep working in the EVA. The remote control and the Arduino never needed to have their power supply changed or recharged. It was really efficient. As I told, it used a 9-volt battery, the RC controller, and also the Arduino. And it was never needed to recharge. We tested after each EVA the voltage running on the battery, and it was still pretty good, near the 9 volts. But the Rover LiPo battery was needed to be recharged because it was a highly consumption of the battery was being done in each EVA, so we had to recharge it every time, so all the functions of the rover could work pretty well in the next EVA. So the conclusions we saw in this test was that this kind of device could be really helpful in the early Mars expeditions, because this kind of devices like the DIM model is a easy, fast, and economic way of deploying a GPS system in the Martian soil. And these kind of robots can fix a problem that they already had, that they can be broken, or the high winds could moving them from their places. Also, another solution that is provided by this rover is that we can make flexible networks with our whatever we want to do. In each EVA, we may want a different range of a system to know the location of each astronaut. So with this kind of robots, we can fix that. So thank you. That was everything. So do you have any questions? Yeah.
You were concerned about the wind.
Yeah.
On the slave devices.
Yeah.
On Mars, would that be a problem?
Actually, in Mars, the density of the air is 1% than here on Earth. It is the high winds there are not the problem. The problem it is right here. But anyway, it is a big problem. It is quite a problem, because if they are not correctly installed, if one of these devices moves, the whole system goes down. Let's image a situation like the Martian movie. It is that the scene where Matt Damon is lost. That can happen in Mars, actually. That can happen, but just in case of any situation we have to face, that we have to know every astronaut location. We have to be sure that the wind may not be that hard, but we have to know that the system is not going to fall down, and we have a way to recover the whole system. That will be the case of deploying this kind of robots if one of these devices went off, to bring a new one and recover the whole system. Yeah.
I saw that you had you were concerned about the size. Was it just like, I guess, not in your budget to do something like using surface mount components on an actual printed circuit board?
Do you mean with the RC controller?
Yeah.
Actually, we saw a lot of internet modules on internet, and we thought about using the one we used there because it was cheap, and the range, that we could use the controller was about 100 meters. We didn't need much more than that. That's why we used that kind of components, because we didn't need something better than that. But that was enough for us.
No worries.
Yeah. Yeah.
Since the space suite
Yeah.
was developed by the team, or
It was already at the MDRS. It was already there. Actually, the MDRS is now facing. They are changing everything, so I think that the spacesuits are going to change too. Any other questions? Okay, thank you then.